Hi guys, good morning, good evening, so wherever you are. So in this lecture, we'll talk about transition elements. So we'll talk about transition elements and their coordination compounds. So whenever we talk about transition elements, so always remember the fact that transition elements are elements simply the D block elements and F block elements. So the combined elements are called transition elements. So we'll see the properties of transition elements, what are inner transition elements, and we'll see the coordination compounds and the theoretical basis for bonding and the properties of these complexes. So let's start with transition elements. So transition elements can be classified into two types. So the common general transition elements, the other group called the inner transition elements. So the D block elements in the periodic table between the group 2A and 3A, these elements are called the transition elements. They are generally given the name 3B to, they are generally given the name 1B to 8B, provided they start with 3B and until they go until 8B, and then you get 1B and 2B. But even in 3B and 4B, so 8B contains 3 rows combinedly called 3 columns, combinedly called 8B. So we'll discuss more about it. And the next group is the inner transition elements or the F block elements. So these are found under the periodic table. These are found under the periodic table. Now, whenever you see transition elements, all of them are metals. All of them, all of them are completely metals. The differentiating factor between this is that if you remember in main group elements, so main group contain S and P block elements. So these elements are generally sometimes metals and sometimes non-metals. But when it comes to D block and F block elements, these are completely metals. So, and one special group in F block, there are 2 rows of elements. So the first row are called actinides. So the first row are called lanthanides. And the second row are called actinides. So lanthanides because they are the elements after lanthanum. Remember that lanthanum is not a D block element, but elements after the lanthanum are called lanthanides. Actinides are elements after actinum. So this actinium is also not a transition metal. So in D block elements, you will see multiple elements. So this is the biggest group of elements in transition elements. So we'll talk more about them as we go along. But remember lanthanides and actinides. What are the common properties of transition metals? So first property we already said is that all transition metals are metals. So whereas main group elements can be metals and non-metals. So because they can be metals and non-metals, so the chances are they can be both at the same time. Now, many transition metals are generally colored compounds and they are generally paramagnetic. So, and most main group elements are generally ionic compounds that are colorless and diamagnetic. So again, the differentiation between paramagnetic and diamagnetic. So a paramagnetic is influenced slightly by magnetic fields. So diamagnetic substances are supposed to repel magnetic fields. They are supposed to repel magnetic fields, or you can simply think that they are not influenced by magnetic fields. So these are some elements. For example, scandium, you can find it in earth. Titanium is another metal. Manganese is another metal we use. Cobalt is the element present in vitamin B12. You can see nickel, zinc. Zinc is an element present in an enzyme called zinc carbonase. An enzyme called zinc carbonase. This is the enzyme that is used to remove carbon dioxide. So it is used to remove carbon dioxide from your lungs. And you also have iron, chromium, copper, and also vanadium. These are common metals that you find in your body as well. Some elements are generally found in the body. Those elements are generally called essential metals or essential vitamins. We call them essential materials because they are needed for your body to function properly. So let's go to the next topic, which is how do you calculate the electron configuration, or how do you write the electronic configuration for transition metals. So d block elements have a general condensed ground state configuration. So again, remember, ground state configuration are the configurations when they are not charged, right? So the general configuration is ns2 n minus 1 dx. This is the general configuration for d block elements. You have f block elements. The general configuration is ns2 n minus 2 f14 n minus 1 dx. This is the configuration for f block elements. So it's not exactly f block elements, but these are elements in period 6 and 7 of d block elements. So and then f block elements, you generally end up with ns2 n minus 2 fx. So this is the configuration for f block elements. One peculiar characteristic in transition metals is that transition metals, before losing the d subshell, so before losing electrons from the d subshell, they actually lose electrons from the ns2 subshell. So the ns subshell is the first one that loses electrons. So I'm going to emphasize this point again. So in d block elements, electrons are removed first in ns subshell before the n minus 1d subshell. So before the ns is first removed in ns, and then if there is anything more, then they are removed in n minus 1d. Now, so if you take an element of scandium, we talk about orbital occupancy. Orbital occupancy is the rate at which the electrons are occupied in an element. So what do I mean by that? If you take the first element, scandium, so scandium has an electronic configuration as Z of 21. So if you write down the configuration, the closest element is argon, which is 18, and then you get 3s2, 3d1. So when you write it in the orbital diagram, you have 3s, and then you have so these are the orbital tables that you end up with. Now, when you try to draw the number of electrons, so you get 1, 2, 1. So that's 3 electrons full. So this is for scandium. Now, when you write it for the next element, titanium, titanium is Z equal to 22. Again, you have argon, 3s2, 3d2. So when you write down the same table again, so let me copy this. So we get 2 electrons in the d subshell. So this is the s subshell, this is the d subshell. Now we can continue writing this, but I want to focus on one main metal, two main metals. One is chromium and the other is copper. Chromium has an atomic number of 24. So when you write the electronic configuration, it would generally be 3s2, 3d4. But the problem is that D likes to fill electrons before S, especially if it is close to half filled. So especially if it is close to half filled, it likes to fill it before going to the s orbital. So what happens here? So rather than the electron going directly into the d subshell, the electronic configuration changes to organic, argon 3s1, 3d5. So it will fill up the d subshell before it fills up the s subshell. So focus on the s subshell here. So there's only one electron here. So now when you write the configuration, you get only one electron in the d subshell. So 1, 2, 3, 4, 5. This is one element where you will see that the argon, the chromium, has originally, if you look at it, it should have 4 unpaired electrons, but in originality, it will have 6 unpaired electrons. So it will end up with having 6 unpaired electrons. Now, another element that I want to focus on is copper, which has an atomic number of 29. So now, when you write the configuration, the original configuration would be argon 3s2, 3d9. But, so the configuration is argon 3d2, 3d9, but it does not have, it has about only one electron left to fill in d orbital. So what happens is it fills the d orbital before the s orbital. So it fills the d orbital before the s orbital. So this ends up having an electronic configuration of copper of Z29, ends up having an electronic configuration of argon 3s1, 3d10. So now so it will have one electron at the s subshell. So 1, 2, 3, 4, 5. And if you write out the number of electrons in the d subshell, you end up with a full orbital. So the idea here is in copper, the unpaired electron is in the S subshell. So the unpaired electron is in the S subshell, not in the D subshell as we think of. So this is the two peculiarities I want to notice in period 4 of the transition elements. Now let's take an example of these materials and let's see one by one. Let's take zirconium. So these are the three ones that you have: vanadium 3 plus and molybdenum 3 plus. So I'm not going to do zirconium. You have the answer here. Try to do it on your own and find out the answer. So I'll do vanadium. So vanadium is the third element in the 3D series. So vanadium has it has an electronic configuration of, let me write it down. So vanadium has an electronic number of 23. So when you write the electronic configuration, you have argon 3s2 3d3. So when you write the configuration, so you end up with the two electrons in the s shell and you have the d shell. So you have 1 2 3 4. So you have 1 2 and 3. Now when you write the term vanadium 3 plus, so the question is vanadium 3 plus. So whenever we write 3 plus, it means that it's loss of 3 electrons. Plus represents loss of electrons. Minus represents the gain of electrons. So this is in terms of the charge. Now when we write vanadium 3 plus, where are the 3 electrons losing from? So the first electrons, remember the rule, the first electrons are lost in the s subshell first, and then it goes to the d subshell. So when you write down the electronic configuration, you end up with argon 3d2. So this is the electronic configuration of vanadium 3 plus. So pause the video right here and try for molybdenum 3 plus. So I hope you have the periodic table with you. So try for molybdenum 3 plus. What would be the electronic configuration? Next, what are the trends in the properties of the transition metals? Across a period, these are the following trends that we generally observe. One is the atomic size generally decreases at first and then remains relatively constant in the end of the table. This is because the d electron fills the inner orbitals, so they shield the outer electrons efficiently. So then the forest electrons are not pulled closer by the increasing nuclear charge. Next, ionization energies also increase because relatively little across the transition metals of a particular period. Electronegativities tend to increase slightly, then they will decrease again across the transition metals. This is due to the stability. So this is due to the stability of half-filled orbitals. This is due to the stability of half-filled orbitals. Now, what are the trends that we can generally observe? So these are the trends. So you notice that the atomic radius decreases slightly initially and then remains gradually nearly similar. In electronic negativity, so if you look at the periodic table, it will increase slightly and then it will decrease again. So you will end up with a simple change here. So you have an increase and then a decrease and then another increase directly up. So this is the trend of the electronegativity. Again, the same with ionization energy. As you go across, it increases rapidly and then decreases and then increases again. So this changes that are common. So one within a group. So the trends are also different from each group. So atomic size increases from period 4 to 5, but from 5 to 6 that does not happen. This is due to a property called lanthanide contraction. So for period 6 and 7 elements, it has 32 more protons than its preceding 5-membered group. So what does that do is that it increases the shrinkage and increases the nuclear charge. And it becomes nearly equal to the normal size due to the extra energy level because of the presence of the F sub energy level. That creates the lanthanide contraction. So it basically decreases in size because it's being pulled much closer because of the presence of extra protons. Next, electronegativity trend also increases within a group from period 4 to 5, then generally remains unchanged from period 5 to 6, and as the heavier elements generally have higher electronegativity values. In terms of ionization energy, the values generally increase down a transition group and also counter to the main group elements. So in a main group element, it generally decreases down a group. So ionization energy generally decreases down a group, but in transition elements, it generally increases down a group. So the ionization energy generally increases down a transition group. So density also increases dramatically, and then it starts going down back again. So this dramatically down a group, since the atomic volumes here change very little, while the atomic masses increase significantly because they are much more packed. So the elements are much largely packed. So the more packed they are, the higher the density. So the more packed they are, the higher the density. So these are the graphs that explain the same phenomenon that I just told you about. Next is oxidation states. Most transition elements have multiple oxidation states. So the higher the oxidation element state for the elements in group 3b to through 7b, so that equals the group number. So if you have an oxidation state of 3, it means that it's a 3b group element. If you have an oxidation state of 7, it might be a 7b group element, but that only represents the highest one. So that's the limit to which maximum can happen. Elements in group 8b, 8, group 8b, 9, and 8b, 10 exhibit fewer oxidation states. The reason is because the higher oxidation state is less common and never equal to the group number, only for 8b group elements. And the common oxidation state here is the +2 oxidation state. So best example of that is Zn2 plus. So Zn is an 8b group 10 element. So 8b 10 element. So the common oxidation state that it can exhibit is 2 plus. Next. So these are some of the oxidation state for manganese. So manganese in Mn2 plus has an oxidation state of +2. MnO4 manganese oxide 2 minus, it has an oxidation state of +6. In MnO4 minus, it has an oxidation state of +7. Vanadium, it has +5, +6. Chromium has +6. Manganese has +7. So these are some common anionic states. So the ones that you see in red are the common oxidation states. So one of the elements that has the common oxidation, the highest number of oxidation states, if you look at these are the reds, these are the stable ones. So if you look at the elements, the common one that has more number of oxidation states than the other is manganese. So manganese has the highest number of oxidation states present in it. So in terms of the metallic behavior, the lower the oxidation state, the more metallic its behavior. So ionic bonding is more prevalent when you have a lower oxidation state, whereas covalent bonding is common when you have a higher oxidation state. So in the same way, metal oxides become less basic when you have a larger oxidation state. So it becomes more acidic basically when you have oxidation state. So when the oxidation number or the oxidation state starts increasing, so the acidic behavior also starts increasing. This is the metallic behavior of transition elements. So and also one another one is the reducing strength also decreases across the series. If you look at period 4 elements, so in period 4 across the period, the value starts decreasing as you go down the period. Next is the color and the magnetic behavior. So most main group elements are generally colorless and diamagnetic materials because the metal has no unpaired electrons. So one main group that can help in understanding magnetic behavior is the presence of unpaired electrons. Presence of unpaired electrons. So when you have unpaired electrons, you both get color as well as some magnetic behavior. So most ionic elements are generally colorless. For example, the best example of it is salt. Salt is a colorless crystal, right? So if you take some salts, they are pink. Those are generally made of some kind of a transition element. Next, if you have many transition ionic compounds are generally highly colored and they are generally paramagnetic because they at least have one or more unpaired electrons. So the higher the number of unpaired electrons, the more the metallic behavior, the more the magnetic behavior of the substance. So transition metals with D0 and D10 configuration are also colorless and diamagnetic. One example of this would be zinc. So zinc in its uncharged state is generally a colorless metal and also diamagnetic. So what is generally done to increase its ability is we end up using zinc. So we end up using Zn to find out whether we make it a charged metal so that it can become paramagnetic and it can become color. It can gain some color. So these are some elements and their some compounds that they form and different colors. So notice that most materials have some colors. So notice the different colors that they can form. So one main one to remember is for copper sulfate. Copper sulfate is generally a bluish color. Cobalt chloride hexahydrate is also a reddish color. Potassium ferricyanide is also a reddish color. Sodium chromate is a yellowish material. And zinc sulfate is a colorless material. The reason mainly is because it is in its uncharged or the uncharged state. Now let's go to F block elements and the lanthanides and actinides. So lanthanides are also called rare earth elements because these are rarely found in the Earth's core and they are found in very little amounts. So the atomic properties of lanthanides vary very little across the period and their chemical properties are also really similar. So most lanthanides have the ground state configuration of xenon 6s2 4fx F5D0. And all actinides are generally radioactive and they have very similar physical and chemical properties. And for both lanthanides and actinides, the common oxidation state is +3. So +3 is the common oxidation state found for both lanthanides and actinides. So let's take an example of smerconium. So smerconium is the eighth element after xenon. So you have xenon, the configuration becomes xenon 6s2 4f6. So remember the configuration is the noble gas and you have ns2, you have n-2 fx. So this is the common configuration that we generally find. So if you apply it here, we get xenon 6s2 4f6. And so smerconium here has 6 unpaired electrons. So it's a color, it has color and it is paramagnetic. Now let's come to the main topic in this chapter, coordination compounds. What is a coordination compound? A coordination compound is something that contains one complex ion, which generally consists of a metal cation bonded to molecules or anions. And these molecules are called ligands. So whenever you see a ligand, it generally is bonded to something. It generally is bonded to something. So that's what we call a general ligand. Now, a best example of this is this compound, so which is chromium NH3 taken 6 3 plus. This is an example of a coordination compound. Now, we represent different coordination compounds with a coordination number. Coordination number is the number of ligand atoms that are bonded directly to the central metal ion. So a coordination number is specific for every given metal, and that generally comes from a particular oxidation state and compound. For example, the compound that we just saw has a coordination number of 6. Notice that all the NH3s are connected directly to chromium, and there are 6 of them. So we have that becomes your coordination number. The common coordination numbers are generally even numbers, and they are generally 6, 2, and 4. So you have 2, 4, and 6. These are the common coordination numbers that are generally seen. Now, what are the components of a coordination number? So coordination number contains a solidic material and something that dissolves in a solution. So how do you differentiate it? So when you dissolve it in water, it loses the charged material, and the metal solution compound, it stays intact. That is what is called as the complex ion. So it makes an ion where one of them is really complex and it is bonded to simple ions. For example, cobalt, this element here, CONH3, taken 6 Cl3. When you dissolve it in water, forms CONH3, taken 6, 3 plus 3 Cl minus. So the 3 Cl minus becomes the simple ion. This compound is the complex ion. That compound is the complex ion. There are four common shapes that are found with each coordination number. So for coordination number of 2, the common state is linear, where you have two elements that are directly bonded to the coordination compound. And you have square planar, which is a coordination number of 4. It has a plate shape, basically a square shape, where you have a central metal ion and four of the ligands that are connected to it. And another shape is a tetrahedral structure. Tetrahedral is common structure that you have seen already. So you have again the 4 compounds that are connected to the central metal ion. We'll see what conditions it becomes square planar. We'll see what conditions it becomes tetrahedral. And if you have 6 of them, that becomes octahedral. Octahedral is basically a simple construction of a rhombus. So if you connect all the compounds, you get a rhombus. So that structure is generally called as octahedral. Octahedral is when you have a central single metal ion and there are 6 different ligands that are attached to it. Now let's go on to the topic of ligands. What are ligands? Ligands are molecules or anions with one or more donor atoms. So one main characteristic of a ligand is it has donor atoms ready to donate electrons. So these are donor atoms that are ready to donate electrons. Each donor atom generally contains a lone pair of electrons and to the metal ion and forms a covalent bond. So ligands, in terms of the number of donor atoms or teeth, are classified based on them. So we have monodentate, bidentate, and polydentate. So mono, if it has one lone pair, bidentate, sorry, let me write it this way. It has one donor atom. Bidentate if it has two donor atoms. Polydentate if it has more than two donor atoms. If it has more than two donor atoms. So let's see some examples of these ligands. So you have monodentate, bidentate, and polydentate. So a best example of monodentate ions is water. So water is an example of a monodentate ion. So it has the oxygen. So if you consider H2O, so you have oxygen connected to two hydrogens with two lone pairs. So the two lone pairs that are on oxygen, these two lone pairs can be donated. So because that's the reason why it becomes, so because it has one donor atom, so we call this a monodentate ligand. Now there are elements where you have, even if you have a single compound, there might be multiple donor atoms, but they can only donate once. So what does that mean? So if you take an example of thiocyanate, this is an example of thiocyanate. So if you take sulfur here and nitrogen here, there are two elements that have lone pairs of electrons. One is sulfur with two lone pairs and nitrogen with one lone pair. Now the chances are that either sulfur will donate or nitrogen will donate. Remember that it is either or, which means that if one donates, the other does not donate. So these are also called monodentate ligands because there is only one element at any given point of time that donates its electron pair to form the bond. So there are multiple elements like these. For example, one is thiocyanate ion, the other is nitrite ion, which is NO2. You also have cyanide, you have hydroxide ion, which is another example. Next, let's look at bidentate ions. So bidentate means there are two donor atoms. One of the most common examples is a compound called ethylene diamine, or the short form is EN. So it's basically CH2 bond CH2 bond NH2 bond NH2. So the nitrogen here, the nitrogens that are here, each can donate its lone pair and form a bond. Right, the nitrogen here acts as a donor. Here this nitrogen can also act as a donor, and they can both donate at the same time. Right? So these elements are called bidentate ligands. So these type of elements are called bidentate ligands. So one of those examples is ethylene diamine, so written as a short form EN. The other example is an oxalate ion. Oxalate ion is C2O4 minus, O42 minus. This is an example of another ion. So where you have two carbons that are combined with oxygens. So this is an example of an oxalate ion. Here, these two oxygens are the ones that are ready to donate their electron pair. So this way, this is also becoming a bidentate ion. Next, let's look at chelates. So bidentate compounds and polydentate compounds, because they bond to, they have more than one donor atom, they give rise to ring structures in the complex ion formation. So a complex ion containing this type of a structure is called as a chelate. So because the ligand seems to grab the metal ion like claws, so you basically have like a claw structure, so bonding to the metal ion. So these types of elements are generally called chelates. So I'm sorry, we did not discuss polydentate. Polydentate, another example of that is EDTA, ethylene diamine tetraacetic acid. So this is tetraacetate, ethylene diamine tetraacetate ion, or EDTA. This is an example of a polydentate ion. So in EDTA, there are 6 different elements that can act as donors. If you take a triphosphate has three different elements that can act as a donor atom. And another one is diethylene triamine. You have three nitrogens that are ready to donate their electrons. These are compounds that are generally called polydentate ions. So chelates are only formed when the ligands are either bi or poly. So either they are bidentate or polydentate. Now, how do you write the formulas for coordination compounds? So a coordination compound can consist of a complex cation with a simple anionic counterions, or it can consist of a complex anion with simple cationic counterparts, or a complex cation with a complex anion as the counterion. So when writing the formula of a coordination compound, first thing to remember is that the cation is always written before the anion, and the charge of the cation, we always have to balance it by the charge of the anion. And if you have neutral ligands, that they are written before the anionic ligands, and the formula of the whole complex is placed in square brackets. So this is an example of what are the common rules that we use to write the formula. Now let's take an example. So how do you determine the charge of the metal ion? So let's take a simple compound. K2CO NH3 taken twice Cl4. So this is an example of a complex. So this is an example of a coordination compound. Now let's take the compound. We know that potassium is a cation. So this is the complex part. So this becomes the anion. So when it splits, when you mix it in water, you end up with 2K plus CO NH3 taken twice Cl4 becomes 2 minus. So now you have a complex anion. So you have a complex anion. Now, by taking the complex anion into consideration, how do you calculate the charge? So we know that the anion itself has a charge of 2 minus because it has to counteract the positive cation. Now, there are two neutral ligands. So the two neutral ligands are NH3s, right? NH3 is a neutral ligand, and there are 4 Cl minus ligands. So there are 4 Cl minus ligands. Now taking that into consideration, so what is the charge of the complex ion can be written as the charge of the metal ion plus the total charge of the ligands. So we do not know the charge of the metal ion, let's call it X, plus there are two different neutral atoms, so 2 into 0, plus you have 4 different chlorine atoms, so 4 into minus 1. So the charge of the complex ion is already noted, which is negative 2. Now find X, so it becomes minus 2 is equal to X plus of minus 4. So X becomes minus 2. So if minus 4 goes this side, so you have plus 4. So you get a charge of plus 2. So you get a charge of plus 2. So now we know the central metal ion here is cobalt. So cobalt here has a charge of 2 plus. So this is the central metal ion in this coordination compound. So this is how you can calculate the charge on the central metal ion. Next, So let's try another one. You have CONH3 taken for Cl2 and Cl. So notice that we always write the cation first. So this is the cation. So this is the anion. So here we have a complex cation. And all of it are inside. So everything inside. So NH3 and Cl are both ligands. Right. So you have, if you put it in water, you get CO NH3 taken for Cl2 plus Cl minus. So because there is one minus, so it becomes plus. So the complex cation that we have is CONH3 taken for Cl2 plus. Now use the same formula, so which is the charge of the complex ion is the sum of the charge of the metal ion plus the total charge of the ligands. Now, what is the charge of the metal ion? So the charge of the metal ion here, we do not know that, so let's call it X. So let's take the total charge of the ligands. So there are 4 neutral ligands. So NH3 here is the neutral ligand. Cl is the charged ligand. So it has a charge of -1. So there are 2 of them. So it becomes 4 times 0 plus 2 times -1 is equal to +1. So the complex ion charge is +1. So we use that +1 here. So now +1 is equal to X minus 2. So X becomes +1 plus 2. So you get +3. So the central metal ion cobalt has a charge of 3 plus. So in this coordination compound, the central metal ion has a charge of 3 plus. Now, so take another example of platinum. NH3 taken twice, Cl taken twice, Cl2. So now here calculate the charge of the platinum. So pause the video right here and try to solve this problem and calculate the charge of the platinum metal. So also take a pause in this slide as well. You also have sodium. You have these 3 compounds. So try and answer and try to find these 3 compounds, the central metal ion's charge, and also find the coordination number. So also remember that coordination number is the number of ligands. So I'll do one of them. For example, in this, if you take the square brackets, everything inside it is connected to the metal is a ligand. So here OH is a ligand. There are 4 of them, so there are 4 ligands. So the coordination number is 4. Now in this way, try for B and C. How do you name coordination compounds? So the cation is named always before the anion. Within the complex ion, the ligands are named in alphabetical order before the metal ion. So this is within the complex ion. If you have an anionic ligand, we drop the ide and we'll write O after the root name. A numerical prefix is used to indicate the number of ligands of a particular type. So prefixes do not affect the alphabetical order, so it can be bis, tris, or tetrakase. If you have 2 of them, it's bis, 3, tris, 4, tetrakase. Now, a Roman numeral is used to indicate the oxidation state of the metal that can have more than one state. If you have only used this when the transition metal and the transition element has multiple oxidation states. Next, if the complex ion is an anion, we drop the ending of the metal and we'll write 8. So an example of that would be if you take H2O, we write aqua, NH3 is written amine, CO is written as carbonyl, NO is written as nitrosyl, F fluoro, so ide becomes oro, so chlorine becomes chloro, bromine becomes bloro, you have OH becomes hydroxy, CN becomes cyano. So these are the common anionic ligand names and neutral ligand names. Next, for the metal complex anionic metals, the metal ions, iron is written as ferrate, copper is written as cuprate, lead is written as plumbate, silver is written as argentate, gold as aurate, tin as tannate. So let's try the first example, Na3AlF6. So the first rule is cation is named before the anion. So here we know that sodium is the cation, so the first name comes sodium. Next, inside the ligand name, we write the first ligand names. What are the ligand names? So you have a fluoride ligand. So you have a fluorine ligand. So we'll remove fluorine and we'll write fluoro, but there are 6 of them, so we can write hexafluoro. And there is aluminium is the metal. So if we remove em and we write 8, so it becomes aluminate. So it becomes sodium hexafluoro aluminate. So this is the name of the compound here. Here I'm not going to write the oxidation state for sodium because sodium has a fixed oxidation state. So aluminum has a fixed oxidation state of +3. So there is nothing more than that. So we can write simply that name. Next, let's try another one, which is CO, En taken twice, Cl2, NO3. So this is the compound that is given. Now we know that this is the anion and this is the cation. So always we name the cation first. Now in terms of the cation, we have cobalt, we have ethylene diamine, and we have Cl2. Notice that En represents ethylene diamine. Now let's start based on the alphabetical order. You have 2 ligands, you have chlorine and you have ethylene diamine. So chlorine will end up being written as chloro. So let's start with alphabetical order, chloro. There are 2 of them, so we write dichloro. And there are 2 ethylene diamines, so we cannot write di in amine, so diethylene diamine, so we write it as bis. So bis, and in brackets write down ethylene diamine. So you have cobalt, so that's the compound that you have. So use the cobalt here, but we know that cobalt has multiple oxidation state. We want to know the oxidation state for cobalt. Now let's check each of them. We notice that ethylene diamine is neutral, chlorine has a charge of -1. So now we know that the metal has a charge of +1 because NO3 has -1, so it becomes +1. So +1 is equal to X plus 2 times 0 plus 2 times -1. So it becomes X minus 2 is equal to +1. So X becomes +1 plus 3. So +1 plus 2. So it becomes +3. So the cobalt here has 3 plus charge. So we write cobalt 3 and we have NO3 here, so we write nitrate. So this is the name for the final compound. You don't need to write the hyphen here. So dichloro bis ethyl diamine cobalt 3 nitrate. So this is the compound that you end up with. Next, so in the next one they have given you tetraamine bromochloro platinum 4 chloride, and you have hexaamine tetrachloroferrate. Now I'll do one of them, so you try the other one at home. So let me do C. Now always write the cation before the anion. So the anion is chloride, so let's write Cl, right? And it has an oxidation state of 4. We do not know the total ion's oxidation state. Do not write that right now. So don't write anything right now. So let me write down the compound separately. So you have tetraamine bromochloro platinum 4. For tetrachloro platinum 4 chloride. So this is the name given. So we know that the outside one is fluoride, and there is bromine, there is chlorine, and there is one of each, and there is tetraamine. So NH3, there are 4 of them, and platinum is the metal. Now we can write that based on the order. We have platinum, NH3 taken 4, BrCl. So this is the complex anion, and chlorine here, Cl minus, is the complex. So the anion here, this becomes the complex cation. Now we want to know the charge of this complex cation. So for that we need to know platinum's oxidation number first. So the charge on the metal cation is 4. So because it's 4 and it's a metal, we can write it as Pt4 plus. Now to calculate the charge of the complex ion, the charge of the complex ion is the charge of metal ion plus the total charge of the ligands. So there are 3 different ligands. You have NH3 ligand, Cl and Br. NH3 has a charge of 0, Cl has -1, bromine has -1. Now the charge on the metal ion is 4 plus, so plus 4 plus, there is total change of, there is 4 of amine, so 4 times 0 plus 1 times -1 plus 1 times -1. So now when you write the full charge, it becomes 4. So this becomes 0, this becomes -1 and -1, so you get -2. So 4 minus 2, it becomes plus 2. So the charge on the complex cation is 2 plus. So if there are 2 pluses here, then compensated there should be 2 minuses. So the total compound becomes platinum, NH3, BrCl, Cl2. This is the formula for this compound. So use this as a basis and try solving the next one, which is hexaamine cobalt 3 tetrachloroferrate 3. So try this as an example. If you do not know, there is an answer at the end of the slide. So use that as your answer.